Done nothing implicitly yet. You've not used the technique in this section yet, really. All you've done is done a chain rule on the left-hand side, one chain rule. Okay? The implicit part will come next. Now, what about the right-hand side? What's the derivative of x? What's the derivative of x with respect to x? 1. What is the derivative of y with respect to x?
dy over dx.
That's right. Our symbols we're looking for, right? We're trying to find that thing inside this junk. So it happens to appear one time on that side, and it's going to appear again on the left-hand side. Okay, so the equation we solve in a moment will be a little more.
Wait, why did you do that to the y? Because it's inside of the x.
Why do we do what?
dy dx at the end.
Because this was y. I'm applying d dx to y. So that is dy dx.
Yeah, but why didn't we just do like what you did to x? Because you're adding it?
I mean, why is it not 1?
Yeah.
Because y is a function of x. It's not a constant.
Oh, and the x is...
X. Oh, sorry, I should not say it's not a constant. I apologize. Because y is a function of x, the derivative of y with respect to x is just this pile of symbols, which we do not know what that is. Because we don't know how y is related to x. But this, the derivative of x with respect to x, is always just 1.
Oh, okay.
The derivative of anything with respect to itself is always 1. Okay? On the left-hand side, we still need to take this derivative. And it's a product rule now. This is the function x times the function y, right? So you'll have secant squared xy times a product rule, okay? So the first function is x. So you need to take the first times the derivative of the second. What's the derivative of the second?
dy.
It's our symbols, dy dx. That's right. dy dx. Plus second, that's the y, times the derivative of the first. 1. That's right. Boom. Equals the same stuff over here. So there he is, and there he is. And that's the thing we're trying to solve for now. We're trying to solve for dy dx. What was that? Okay. So how are you going to get them together? Right? You need them on the same side of the equation, correct? That's how you solve for something. Same side of the equation, and everything else on the other side.
Divide.
If you divide by secant squared xy,
No, the other parts that are both on the same side. Oh, but...
oh, saying divide this over here? No. You don't want to do that. Distribute. You want to distribute. It looks a bit cumbersome at first, and it is, but it's going to get you where you need to go. So x secant squared xy dy dx, right? This multiplied into this one, with the x out front, just for aesthetics, plus y secant squared xy. Y secant squared xy. The right hand side stays the same, 1 plus our derivative we're looking for. So anything that now has the dy dx in it, you're going to get together on one side. Everything that does not, you're going to get on the other side. So I will choose to subtract this dy dx over here, and I will subtract the y secant squared over here. Okay? X secant squared xy dy dx minus dy dx, now on the same side, and 1 minus y secant squared xy. Now that you have the thing you're looking for on one side of the equation only, and everything else on the other side, you can now factor off the thing that you're trying to find from that side of the equation. So now read dy dx times x secant squared xy minus 1. Right hand side stays the same.
We're factoring the left side?
Yep. Factoring off the piece we want, right? Factor off the dy dx. So we get secant squared, we get x secant squared xy minus 1. And that equals the right hand side, 1 minus y secant squared xy. Alright, then now just divide. Remember, this is a product there, right? So you divide off by your x secant squared xy minus 1. So now we finally have dy dx. factoring this problem in the computer folder. All right.
You have dy dx minus dy dx in problem.
No, I have something times dy dx minus dy dx. So I'm factoring out the dy dx. Remember dy dx, all those pile symbols, it is a number, it's a quantity, because it's your derivative, right? Or it's a, actually, sorry, it's not it is a quantity ultimately, but it's a function. It's its own little function there.
So you still have minus dy dx.
No, you have minus 1. If you factor dy dx from both of these, you get x secant squared xy minus 1, right?
Well, can't you just factor out the one?
Factor out the what?
The one?
The
like,
1?
I mean, can't you take out the one on the other side?
What am I taking out?
Oh. I was asking if you could take out the one, because there's a one at the top and
This
the one
one?
at the bottom.
This one?
One's negative, one's positive.
They don't require me to take out my brain. What do you mean? No, you can't do that.
Oh, I was just.
Oh, no, that's subtraction. No, that's addition subtraction. You can't just
Yeah.
Okay.
start canceling like that. That's, yeah. Oh, who taught you pre-calc? What kind of idiot taught you pre-calc,
You
Cornado?
did.
Yeah.
Because
whatever.
if you cancel out, then what's left with the negative?
Well, yes.
Alright, anywho, we're supposed to find this at 0, 0 now. So dy dx at the origin.
Wait, what are we doing right there?
We're supposed to find this. This is the slope anywhere on this relation. We need to find it at the origin, specifically at 0, 0. So we're just plugging 0, 0 now. So dy dx at 0, 0 is going to be 1 minus 0 secant squared 0 times 0 over 0 secant squared 0 times 0 minus 1. So it looks like, well, you got times 0 here, so it's going to go there. There. Give me what? Yeah. So you have 1 over negative 1, which resolves as negative 1. So there's our slope, negative 1. What do you say? Everybody always says that. There's always some problem, somebody hits, and they're like, all that work for 5, right? All that work for 2. Yeah, I guess.
Yeah.
Here's what it is.
Wait, what is negative 1?
Slope of this curve at the origin, at 0, 0. How you guys do with implicit? A little confusing?
Yep.
That itself is a function.
Chapter
That
3 is confusing already.
What's a function?
That right there is a function, right?
It's a relation.
It's a relation, not.
It's a relationship between x and y. It maps out some curve in the plane. It's not a function. Function has only one y for every x. This could have different y's for the same x. No, a relation is the circle itself. A circle is relation.
A circle is.
Circle is relation. But this is not a circle. I don't know. Some crazy looking thing. I don't know. Could do anything. I mean, you don't know. These are not. They're not made for you to understand their graphs now. This is well beyond the understanding of any standard graphing techniques. Why don't we just find the what?
I was looking for a way out of panty lines.